Welcome back to CS201 walkthroughs. My name is Lukash, and today we're going to be talking about evaluating Boolean expressions in Racket. So these B-naughts, bands, and bors, or B-naughts, B-ands, and B-ors. So the first thing I want to look at is these three structs. And if we remember, a struct defines kind of like a new data type that we have to work with. So it says here that a B-naught has one argument, a B-and has arg1 and arg2, a B-or has arg1 and arg2 as well. So just a quick review from how we use structs. If you remember back to the Turing machine p-set, which was the last one, you can access elements of a B-or, a B-and, or a B-naught by their name. So if I say something like I want the B-or arg1 of B-or, let's make up some stuff for the arguments, 1, 2, or it's two arguments. It'll give me 1, arg1. Right there in the order, arg1, arg2, as specified, I can get arg1 with arg1. If I name a B-or, like here, expression 4 is a B-or, I can say give me the B-or arg2 of expression 4. Right, and that is argument 2 of expression 4. Okay, another important thing to know is that when we define these structs, it also allows us to ask if something is that struct. So I can ask B-or question mark expression 4, and it'll return true. So we have this kind of built-in way of testing, need a question mark, what these expressions are. So really quickly, let's go through the definition of how we're going to represent Boolean expressions recursively in Racket, because I think it's important to understand very well. So 0 and 1 represent the constants 0 and 1, and these are Boolean expressions. So if I ask, I think you might have to write a Boolean expression, question mark, like is something a Boolean expression procedure somewhere. If they pass in 1 or 0, you should output true. Racket symbols represent variables and are Boolean expressions. So the main point of these two parts is that it does not have to be a B-and, a B-or, or B-naught to be a Boolean expression. It can be a 1, a 0, or a Racket symbol, and it still is, and you can still evaluate it. Okay, but if expression 1 and expression 2 represent Boolean expressions, then B-naught expression 1, B-and expression 1, expression 2, B-or expression 1, expression 2 represent Boolean expressions as well. So this definition is recursive. A B-or is only a Boolean expression if its arguments are Boolean expressions as well. So something like B-or, hello world 1, this is not a Boolean expression. Right? Because this argument is not a Boolean expression. It's not a 0 or 1, it's not a Racket symbol, and it's not a B-naught, B-and, or B-or. Okay? So let's move on. Here are some examples of Boolean expressions. And I want us to think about how we would evaluate them as a human. So here's an example down here. You have to write a function called eval in environment, which takes a Boolean expression like this and an environment, and it wants to output a 1 or a 0, essentially a true or false, right? Environment 2, and this is up here, environment 2. I've copied over. Okay, so if we were humans, how would we do this? Well, we would look at this outside B-and, and we would say, okay, you know what? Let's uncomment this so we can see the parentheses. This B-and is the outermost kind of classifier, right? So for this Boolean expression to return 1, this must return 1, and this must return 1. So first, let's check if this returns 1. Well, for this B-and to return 1, this must return 1, and this must return 1. So let's check those two. So B-or, W, 0. Well, 0 is not 1, so we have to check W. W in our environment is 1. How did we check that? Well, so we remember that an environment is just a list of entries, right? An entry where a symbol has an associated value. This is the entry key. This is the entry value. You're going to be writing functions that look up the value when given a key. So we determined that W is 1. This BOR is satisfied and we have a 1 here. Let's check this one. Is either U or X a 1 in our environment 2 when we call lookup as a human? Well, I look up U, I find that that's 0, but X is a 1. So this BOR is also satisfied. These are both 1. This evaluates to 1. Now we have to check the second argument of this original B AND. Okay, let's check this B not. B not is true when its argument is false, right? It's a logical swapper. The not of true is false, the not of false is true. So we want this B AND to be 0, to evaluate to 0, for this B not to evaluate to 1. So let's check. Are either Y or Z 0? B not of B AND of Y and Z. So let's look up Y will give us 0. Z will give us 1. The B AND of those two is 0, right? For B AND we need both of them to be true. Here both of them to be 1 in this case. Here only one of them is 1. This B AND returns 0. This B not returns 1. Since this B not and this BOR both return 1, this B AND and this B not return 1, this B AND returns 1, and our function returns 1. Okay, so you're going to be doing this, as you might have recognized, recursively, right? In the same sort of structure that we had with tree recursion, except for in tree recursion, we separated the car and the cooter of a tree, and then mashed the results together. So for a problem like sum, we would, for example, for sum tree, we took the sum of all the elements in the car, all the elements in the car, and the sum of all the elements in the cooter, and added those. Okay, well, a Boolean expression evaluation is very similar. We need to separate the arguments if it's a B or B and evaluate them separately in the environment. So that sounds like recursion, right? We'll say something like, if it's a B or, then we need one of these two recursive calls to return true. If it's a B and, we need them both to return true. But let's think a little bit more about what the recursion will look like. What are our base cases? Our base cases are the same as base cases for Boolean expressions, right? If something is a 0 or a 1, a racket symbol, we don't need to recurse. We know whether it evaluates to 0 or 1. The same is true for racket symbols. We can look them up and determine whether they represent 0 or 1. We don't need to recurse in those cases. So racket symbols or 0/1. This is made a little bit trickier. Recursive cases are B nots, B ands, B ors. So we've talked about what to do if you find a B and or a B or, right? So you recurse on its two arguments. For B not, you're also going to recurse on its argument, but you're going to switch whatever you get from that, right? Because B not, we said, is a logical sort of swapper. If you give it a 1, it'll spit out a 0. If you give it a 0, it'll spit out a 1. So it's made a little bit tougher, though, because sometimes there are unspecified variables. So we need to check if we can do something like, so if we have a B and like this, a B and 1 hello world, if we run eval and environment on this, we cannot simply say this is a B and, run on its arguments separately, and then take the and of those. Put in caps. Cannot just run recursive function on arguments need to know first if there are unspec variables. So this is similar to in prod tree, right? In prod tree, we couldn't multiply the prod of the car and the prod of the cooter until we checked that they both returned numbers and not what was it, like no there's some output, and we'll say that they both returned numbers, right? There's some output if there were no numbers in the tree. So similarly here, we have to know, well, are we going to be taking the AND of two Booleans as we want to be? Okay, so we can check in the same way. Can check the recursive calls to see if they return Boolean expressions before we try to evaluate. Okay, I'll let you kind of mull through that as you go through writing these functions. I hope I've helped you understand a little bit what these Boolean expressions be not, be and BORs are, as well as these bracket symbols and the constants. I hope I've helped you understand how to tackle some of the problems in homework 4. Thanks for watching this video walkthrough. If you have any questions, as always, come to office hours, post on the Piazza, or email the CS201 help email. And I hope to see you in the next video.